Hello everyone, I am delighted to continue learning the concept of geometric sequence with you all today. In the previous learning, we analogized the arithmetic sequence and obtained the concept and general formula of the geometric sequence. Can you accurately write the general formula for the geometric sequence? Yes, it should be an n equal to a 1 multiplied by n minus 1 power of q, where n belongs to n star. Let's try using the general term formula of the geometric sequence to solve practical problems together. Example 4. Purchase a certain financial product for 10,000 yuans for 1 year. How much interest can be earned over 12 months if compounded at a monthly interest rate of 0.4%? Accurate to 1 yuan, if the quarterly compound interest is deposited for 4 quarters, what is the interest rate for each quarter, and the interest settled quarterly is not less than the interest settled monthly? Please be precise to the -5 power of 10. The compound interest problem refers to calculating the sum of the interest from the previous period and the principal, and then calculating the interest for the next period. Taking the deposit of a yuan as an example, at the end of the first period, we will calculate the interest by multiplying the principal a yuan by the interest rate, and then add the principal a yuan. By extracting the common factor, we can obtain that the total principal and interest for the first period is a times 1 plus r. At the end of the second period, we multiply the principal by the interest rate r to get the interest, and then add the principal multiplied by 1 plus r. By rearranging, we obtain that the principal and interest sum at the end of the second period is a times 1 plus r squared. By analogy, we obtain the principal and interest sums at the end of the third and fourth periods. Through observation, we find that the principal and interest sums of each period constitute a geometric sequence. The first term of this geometric sequence is a times 1 plus r, and the common ratio is 1 plus r. The general term formula can be obtained as a n equals to the first term a times 1 plus r multiplied by the common ratio 1 plus r raised to the power of n minus 1, which after rearrangement is a times 1 plus r raised to the power of n. This question is a practical problem. By combining this example with the geometric sequence an, we can transform this practical problem into a mathematical one, thereby finding a solution. Let's analyze the conditions for the first question. If 10,000 yuans is used to purchase a certain financial product, then the corresponding principal A is equal to 10,000 yuans. If the monthly interest rate is 0.4%, then the corresponding R is equal to 0.4%. The sum of principal and interest that can be obtained in 12 months is the value of the 12th term A12 of our geometric sequence, and the interest that can be earned in 12 months. We know that interest equals the difference between the total amount including principal and interest and the principal, which is a 12 minus a. This completes the solution process for the first question. Let the principal and interest sum of this money after n months form a sequence an, then the sequence an is a geometric sequence. The first term a1 is equal to 10 raised to the power of 4 multiplied by 1 plus 0.4%, and the common ratio q is equal to 1 plus 0.4%. Therefore, the 12th term A12 is equal to a 1 multiplied by q raised to the power of 11. After substituting the values of the initial term and the common ratio, we can calculate approximately 10,490.7 using a calculator. Therefore, the interest after 12 months is approximately 491 yuans, which is the principal and interest sum of 10,490.7 minus 10,000. Let's move on to the second question. Calculating interest with quarterly compounding is still a compound interest problem. So at this point, we know that this example still constitutes a geometric sequence, which we name Bn. Then we can set the quarterly interest as the common ratio r, which is 1 plus r. The principal and interest after 4 quarters is the value of the fourth term before of this geometric sequence. The interest settled after 4 quarters should be B4 minus the principal A. Then the second question asks whether the interest calculated on a quarterly basis is not less than the interest calculated on a monthly basis. That should be B4 minus A being greater than or equal to a 12 minus A from the first question. So let's go through the solution process for the second question. Let the quarterly interest rate be r. The sum of principal and interest after depositing the money for n quarters forms a sequence Bn, which is also a geometric sequence. Its first term B1 equals 10 to the power of 4 multiplied by 1 plus r, and the common ratio is 1 plus r. Therefore, B4 equals the first term B1 multiplied by the common ratio to the power of 3, which after rearrangement is 10 to the power of 4 multiplied by 1 plus r to the power of 4. Thus, with quarterly compound interest, the interest after depositing for 4 quarters is 10 to the power of 4 multiplied by 1 plus r to the power of 4 minus 10 to the power of 4 yuans. Let's solve this inequality. Through calculation, we can obtain that r is greater than or equal to 1.206%. Therefore, when the quarterly interest rate is not less than 1.206%, the interest calculated quarterly is not less than the interest calculated monthly. Applying mathematical ideas, methods, and knowledge to solve practical problems is the process of mathematical modeling. This problem involves abstracting and simplifying real-world issues to determine the mathematical formulas corresponding to principal, interest rate, principal, and interest. By applying the knowledge we have learned, we have sorted out the relationships between variables. The compound interest problem is transformed into a corresponding geometric sequence model. Then we use mathematical methods to solve it, and use our model to explain various phenomena and patterns in real life. Next, let's look at example 5. Given that the first term a1 of the sequence n is equal to 3, and if the sequence n is an arithmetic sequence with a common difference d equal to 2, prove that the sequence 3 raised to the power of n is a geometric sequence. If the sequence n is a geometric sequence with a common ratio q equal to 1/9, prove that the sequence with base 3 and the logarithm of n is an arithmetic sequence. Let's first think about how to prove that a sequence is a geometric sequence or an arithmetic sequence. Yes, we need to prove it starting from the definitions of arithmetic sequence and geometric sequence. Can we prove that a sequence is an arithmetic sequence using a partial term, such as a 2 minus a 1 equals a 3 minus a 2? It cannot, because it does not meet the definition of the geometric sequence, which states that from the second term onwards, the difference or ratio between each term and its preceding term is equal to the same constant. So what do we use as proof? We use a n for the nth term to prove it. So let's look at the first question. Since we know that the first term, a1, is equal to 3 and the common difference d is equal to 2, we can write n as 2n plus 1 according to the general formula for an arithmetic sequence. We set bn equal to 3 raised to the power of n, and substituting n as 2n plus 1 gives 3 raised to the power of 2n plus 1. Therefore, the ratio of the next term to the previous term in the sequence bn. After substituting the formula, we can calculate that it equals 9. This means that from the second term onwards, the ratio of each term to the previous term in the sequence bn is equal to a constant 9. Also, since b1 is equal to 3 raised to the power of a 1, that is, 3 raised to the power of 3 equals 27. So the n power of the sequence 3 is the geometric sequence with 27 as the first term and 9 as the common ratio. Let's move on to the second question. Since the first term, a1, is equal to 3 and the common ratio, q, is equal to 1/9, we can use the general formula for the geometric sequence to write n as the first term, 3, multiplied by the common ratio, 1/9, raised to the power of n minus 1. Since 1/9 is equal to 3 raised to the power of minus 2, we can simplify this to 3 raised to the power of 3 minus 2n. By taking the logarithm base 3 of both sides of this equation, we can obtain that the logarithm base 3 of n equals the logarithm base 3 of 3 raised to the power of 3 minus 2n. According to the operational properties of logarithms, we can calculate that it equals 3 minus 2n. So the difference between the last term and the previous term of this sequence is equal to -2. That means from the second term onwards, the difference between each term and its preceding term is equal to the same constant -2. Since the logarithm of a 1 to the base 3 is equal to the logarithm of 3 to the base 3, which is equal to 1, we know that the sequence of a n to the base 3 is an arithmetic sequence with a first term of 1 and a common difference of -2. Based on the previous proof, has anyone thought about whether the sequence of b to the power of a n is necessarily a geometric sequence if we know that b is greater than 0 and not equal to 1, and the sequence a n is an arithmetic sequence? And if the sequence a n is a geometric sequence where all terms are positive, does the sequence of the logarithm of a n to the base b necessarily form an arithmetic sequence? We attempt to apply the same proof approach to generalize the conclusion from the special case to the general case. Let the first term of the arithmetic sequence a n be a 1 and the common difference be d, then the ratio of b to the power of a n plus 1 to b to the power of a n is equal to b to the power of d. After substituting the general term formula, we can calculate that it equals b to the power of d. Therefore, the sequence of b to the power of a n is a geometric sequence with b to the power of a 1 as the first term and b to the power of d as the common ratio. Similarly, let the first term of the geometric sequence n, where all terms are positive, be a, and the common ratio be q. Then, the logarithm of a n plus 1 to the base b minus the logarithm of a n to the base b equals the logarithm of a n plus 1 to the base b over the logarithm of a n to the base b. Since the sequence a n is a geometric sequence, a n plus 1 divided by a n equals the common ratio q. Therefore, this formula equals the logarithm of b to the power of q. We obtain that the logarithm of the sequence n to the base b is an arithmetic sequence with the logarithm of a 1 to the base b as the first term and the logarithm of q to the base b as the common difference. From this, we have established the relationship between the arithmetic sequence and the geometric sequence. Then we wonder if we can transfer some properties of the arithmetic sequence to the geometric sequence. So, what are the properties of the arithmetic sequence? Let's recall that in the arithmetic sequence n, we have learned that if m plus n equals s plus t, then am plus n equals s plus a t. So we can deduce from the geometric sequence n, where all terms are positive, that the logarithmic sequence of a n with base b is an arithmetic sequence. When m plus n equals s plus t, the sum of the mth term and the nth term of this sequence equals the sum of the sth term and the tth term. According to the logarithmic operation rule, we know that the logarithm of am multiplied by n with base b equals the logarithm of a multiplied by a with base b. Therefore, we can obtain that am multiplied by n equals s multiplied by a t. That is to say, in the geometric sequence n, if m plus n is equal to s plus t, then am times n equals s plus a t. Now let's prove it in detail. Let a n be a geometric sequence with common ratio q. We can express am, a n, a s, and a t in terms of the first term a 1 and common ratio q using the general formula of the geometric sequence. Am multiplied by a n can be obtained by rearranging as equal to the square of a 1 multiplied by q raised to the power of m plus n minus 2. Similarly, a s multiplied by a t equals the square of a 1 multiplied by q raised to the power of s plus t minus 2. Since the given condition is that m plus n equals s plus t, we can conclude that am multiplied by n equals s multiplied by a t. This is an important property of the geometric sequence. Through the proof just now, we can see that this property does not require all terms of the geometric sequence to be positive. Let's summarize what knowledge and methods we have learned in this class. We have mastered the general formula of the geometric sequence and applied the concept of equations to solve related calculation problems of the geometric sequence. We also utilized the idea of modeling to transform practical problems into mathematical ones and solve them. Through the transformation, we derived an important property of the geometric sequence n, which states that if m plus n equals s plus t, then am times n equals s times a t. That concludes today's lesson. Goodbye, everyone.